Hello, everyone, and welcome to our webinar, our second webinar in our series about drone and drone technologies and scientific research. And my name is Alexey Smirnov. I'm a regional director for SPH Engineering. And today we'll be speaking about snow and ice studies and everything about mountains, glaciers, ice, snow, and everything around it. And today we have two wonderful guests. That's Robert Delleske from GeoResearch. He has a great expertise in every type of remote sensing, like TLS, ALS, photogrammetry, satellite data, drones, GPRs, and he's been working in this industry, in this area, I believe, for the last decade. Hi, Robert. That's very cool to have you here today. And the second guest today is Bastien Dupuy. He's a research scientist at SINTEF, and he's also a great expert in nature hazard applications, avalanche forecasting, and remote sensing. And he also has a huge experience in drones, photogrammetry, LiDARs, GPR, and how to combine all this data together and how to use them to conduct all this scientific research. And a bit about housekeeping today. All of you can use Q&A section and Q&A capability of Zoom. Please leave your questions, ideas, suggestions, insights, and that would be great to discuss them. Also, we have dozens, maybe even hundreds of your questions during registration, and we'll try to highlight most of them. What else? If you want to participate in this discussion, please raise your hand. I mean, virtually by using Zoom feature. And yeah, if you have time, we'll let you also speak and share your ideas and insights. What else? Before we start and before we go to presentations, I'd like to have a short poll for all of you, just to understand who is our audience today. So what we see, a lot of people today from the scientific world, and yeah, welcome all scientists, all researchers. We are glad to see you here today. And yeah, that's interesting that almost a half of our audience already using drones, and that's great. And I would love if you can share your experience today also in this Q&A section. But there are 16% who is from the scientific world, but don't use drones yet. I hope after our session today and after all our next webinars, following webinars, you'll change your mind and you'll start using drones more actively in your research. And those who came for new knowledge and to know more about drone technologies, I believe you'll be smarter after this webinar today, and you'll know a lot of new things. Okay, thank you everyone for polling. And now it's time to go to short presentations of our guests, just to explain the whole idea of what is their research is and how it all works and how drones are used. And after that, we'll have a short discussion. As I said again, please leave your questions in Q&A section. And after all presentations are done, we will go through. Robert, the floor is yours.
Yes, thank you for the invitation and to present here. And I want to talk about some of our high alpine UAS project, Salzburg in Austria, how we're using it. And first, I want to give you a brief introduction about GeoResearch. We're a non-profit research institution from Salzburg in Austria. We were founded 2016, so we're still a rather young institution. Our team is very interdisciplinary with a core expertise in geomorphology, informatics, and remote sensing. And our research projects, we're investigating natural hazards in alpine regions, and therefore we have a lot to do with climate change impacts, and which are particularly served also in high alpine environments. First, I want to show you is one of our biggest and long-lasting project. It's our open air lab, Kitzsteinhorn. So we're having this opal since 2010. The basic founding is coming from the Gletscherpan Kaprun, so we have a really great infrastructure, as you also see here on the right-hand side, that we can use. We can use a cable car and so on. And this opal we're using as an open scientific exchange network. So we're working with different institutions together to do this research there. For instance, TU Munich, ETH Zurich, AGE Alp, Geosphere Austria, and so on. And we're doing our research here in different levels. So we're doing subsurface monitoring with deep boreholes, shallow boreholes, different geophysical methods on site there. We're doing surface monitoring with laser scanning, a lot of UAS that is getting more and more, and also crack meters, anchors, and also the atmospheric monitoring. From the UAS side, we're using photogrammetric data there since 2016. So we're mapping the glaciers, the rock wall, and we also started GPR surveys with a drone there. So how is it changing there and how we're using the data? So our main part here is the glacier monitoring, and here you can see a mix of data. So the data we have here is mixed from normal flights by planes, photogrammetric data, and from 2016 on, our data made by drones. And what we can see here is that in the 70 years, the glacier lost 65% of its area, and the trend is really going down there. Also, from the volume side, we can see a really big volume change from 2008 to the last year of 43%. And also here we have a combination of all the data. So here this airborne laser scans from 2008 and our data and ground-based data that we've taken in 2019 in combination with the photogrammetric data from the last year. We also started with GPR data from the drone last year, and with the low frequency antenna from SOND. And here in this area of interest, we made first test last year. On the right-hand side, you can see a profile which is 850 meters long. So it took us 3 minutes of flight time in a height of 3 meters, and we got a depth of 50 to 60 meters of the glacier. And as you see on the profile, we could go much deeper. The detailed mapping of this will follow in the next year. So this was the first test. The next project I want to show you is a bit a different side. It's a bit smaller, but also really interesting. It's a subtle cast slide. So it's a really steep catchment. We have around 0.5 square kilometers, and in the half of this area is a release area where we lost around 1 million of cubic meters on material in the last 15 years. And in this project, we want to learn what is the trigger of this project. Probably it's permafrost degradation that we want to know more exactly. And to answer this in this project, we are using different methods. So ground temperature measurements, passive seismic, to see how the processes are going on there, stable isotopes, find out about frozen water, photogrammetry that we're doing there since 2018. And up to next year, we also want to start with GPR in the air layer with a low frequency antenna. Because of this slide there are a lot of rockfall and debris flow events and the impact to the main valley. And there's the impact up to the main valley that is up to 10 kilometers from there. Here you can see on the left side how we are doing our flights since this year with an M300 and the P1 on it. Before this, we had to hike up there, up to this point here, and we had 3 different starting points and flew it all with a Phantom 4. On the right-hand side, you can see animation, how the slide is moving in the last years and the big blocks that you can see in there that are moving are around 10 to 15 meters. The next project I want to show you is an avalanche monitoring. So this project is to detect potential avalanche release zones for big avalanches. This is our first BVLOS project because the area is not accessible in winter by feet or by car or by anything else. So we are using a photogrammetric mapping on snow. We have to fly around 3 kilometers in this direction, can map the area and can fly back. And on the most area, it works very well. But as you can see here, on some areas, in some data sets, you have problems on snow if you don't have enough contrast. So, well, but we get good data. The last project I want to show you is our Stratify project. It's our first airborne GPR project that we carried out together with a lot of help from SPH. Thank you very much for the help, and our project partner Lola, especially with Anna that you can see here on the left. And the goal of this project is the contactless weak layer detection of snow slopes on a larger scale. And we had first results from the last winter with really good results. It worked very well up to 40 degrees steepness in the terrain, and we get really good data on 5 meter altitude at 1 meter per second speed. We also checked the GPR data with snow pits and depth measurements, as you can see here on the slide. So the challenge here is that we want to find the information that we have in traditional snow profiles that you see here on the right-hand side, also in the GPR. So the snow depths work very well, also with the GPR we know, but to get those weak layers, we're using different software modules and also a computer vision approach to find on a larger scale those weak layers. How are the results looking? Here on the right side, you can see our test site from the last year. It's in slope that is getting steeper and steeper. And we made also here the depth measurement that you can see here and the radar data. And this fits really, really good. But in detail, we want to find the weak layers. And as you can see here on the right in the snow profile, there we have these weak layers. And on the right-hand side in the traces itself, we also find the highest altitude, the highest amplitude in this area, and it shows us really well the snow profile. It shows us very well the weak layers that we also see in the snow profile. Okay, so that's it from my side. Thank you for listening. And if you want to find out more about GeoResearch, please visit our website, social media, and hopefully we will meet in person. Thank you very much.
Thank you, Robert. Thank you. Thank you for this short but very elaborate and detailed presentation. I have the first question. Yeah, there are a couple of questions from our listeners, but I'll be the first as a host. I am really interested in your workflow. I mean, in terms of combining all these different types of data, how do you plan your research? How do you choose the most suitable tools in broad terms to conduct this research? And how do you combine all this data, I mean, from LiDAR, photogrammetry, GPR, and satellites, whatever, to get the best data quality, data accuracy, and the best predictable results?
Well, we're not a big research institution. We are only 5 people that are working in GeoResearch, but we have a big network, and the most projects that we're doing in the network. And for each discipline, we have different experts definitely to combine this research. So from my side, I'm from the drone stuff that I'm doing since 2014. But for instance, for the GPR, I need to work together with my colleagues because I had some geophysics in my studies, but I'm not that big expert in GPR, for instance. But I'm going deeper and deeper in it because we're using it in the air now.
Okay, I see. We see. Thank you. Now let's get quickly through questions from our listeners, from our visitors and attendees today. And the first question from Mike Jones, and the next question from Igor Shambretti. I believe they complement each other. How do you use photogrammetry to assess avalanche potential, and what software analysis is used? And that's the first question from Mike, and I believe that's also a relevant question. Yeah. And have you found any reliable solutions to improve the contrast of images taken on snow cover?
Okay, so I will start with Mike's question. So we're just measuring the altitude in the project that I've shown you, and to find the areas where the most snow is falling there and and then we're just doing a GIS analysis. What is the snow high in this area?
Thank you. And have you found any reliable solutions to improve the contrast of images taken on snow cover?
Really important on photogrammetry in areas where you have low contrast. So, for instance, snow in deserts. Also, it's nearly the same. It's nearly the same. There, we're taking the photos every time in the RAW format, and then afterwards we make a pre-processing with the images. If you're just using the JPEG images, in most time you will fail because the algorithms don't find any points there. But it's really if you really have not so good contrast, or also in high alpine areas where we have a lot of shadows, and in the JPEG it will be just black, but after the pre-processing, we will find from the RAW, we will also find really good information there. Yeah. The RAW data is really, really good to use.
And what was the ground sampling distance for this snow photogrammetry project?
I don't really know in detail, but I think it was between 2 or 3 centimeters.
Oh, okay. Okay, I see. Okay, and another question from me. Why drones? And what was before drones? What did you use to perform all this research?
Well, we are using drones because it helped us to get from point measurements that we did by feet and really hard walks into the area, to get really area measurements on a fast way, and also to get reliable and repeatable data. So that's a really big plus for us. Use it, and especially on difficult surface condition, and also on steep slopes or rocky, really big block terrain. It's really good to go in the air to get reliable and repeatable data, because, for instance, the GPR surveys on rock glaciers and on areas like you have seen in the shuttle car, you can't do it that exactly the same way when you're going there by feet. But when you're doing it on the way in the air, you can really do it every time on the same way.
And what was used before drones?
Well, like I've just explained. So we went there by feet and walked through there in such area on
So just
I know my colleague Marcus, they did, I think 2007 or 2008, they made expeditions in Argentina, and they made a lot of GPR profiles by feet, a lot of kilometers.
Oh yeah. Okay, thank you. A question from Syed Hamad Ali. How do you think are drones applicable in narrow waters?
Where?
I bet narrow valleys.
In narrow valleys. Well, it depends a bit on the GPS connection.
Yeah.
And on the size of the drone and the valley. But if you're a good pilot in manually mode, on all time you can use it, definitely. But if you want to fly automatically, it's a question how good GPS connection is. And there I would go there before to check it, and just to see if it's working. But if there's enough space for the drone and some space on the side, manually, definitely. So we're also flying indoor in some applications. But well, you have to be a good drone pilot. You can't do it automatically in some parts.
Okay, thank you. There are some questions about challenges and all these potential hazards, and I suggest we discuss them after Bastian's presentation, because there were a lot of questions about challenges in the mountains and avalanche and everything. But now let's turn to Bastian's presentation. Bastien, please share your screen.
Okay. Yeah, so thanks for the invitation first, and I will show some results from some ongoing research projects. So I'm Bastien Dupuy, I'm research scientist at SINTEF. I'm a geophysicist, and the results I will show is part of some collaborative work with some colleagues at SINTEF. So SINTEF is one of the largest research institutes in Scandinavia. And we have been working with NPRA, which is the Norwegian Public Road Administration, and with colleagues from NGI, the Research Institute in Norway, and from colleagues from University of Grenoble in France. Yes, try to go to the next slide. Just to give you the context, so that's part of two ongoing research projects. One is called GeoDrone. It's an internal strategic project at SINTEF, and where we are basically building drone infrastructure and working on data analysis approaches. And the other one is with Statens vegvesen, so the Norwegian Public Road Administration. And here the goal is to see how drones can be used operationally to take decision, and especially to decide if it's safe to keep the roads open or if the road has to be closed because of avalanche hazard. Let's see if I can remove the top part here. Yes. Just very quickly, why do we use drone for snow and ice measurements? So there are several applications, and Robert has been mentioning some of them, so I can go very quickly. So first, for snow, there are like high spatial variability in snow and snow properties, and this affects the stability, and also these snow properties can change very quickly. And then that's a big challenge for forecasting snow avalanches. The second application is more like for large-scale snow mapping, and it's relevant for hydropower, flood management, water supply. And here in this case, we need information on the snow depth, but also on the snow properties. And then the last one, it's about glaciers, and this is relevant for climate change research, to calculate mass balance, monitor ice thickness, and also for hazards related to glaciers as well. And why do we use drone data? Because it's becoming cheaper and cheaper. It's faster to record data. It's also safer. And then we can cover large area in a short time. And we also have a good accuracy and good data repeatability. What is interesting as well is that we can get data on the surface and also on the subsurface, and that's also help a lot for characterization of snow and snowpack and ice. So yeah, so in the last few years, we have been acquiring a lot of data all over Norway. Yeah, just focus on 3 sites where we have been working. One is called Storidalen. It was like our early test, like easy site, quite flat, at the bottom of the valley. Then we have been working in more steeper terrain and mountainous terrain in Fonbu, which is the avalanche research station, actually in Norway, led by NGI. And then we have been working also in the Jotunheimen mountain range, which is the highest mountains in Norway, where we have glaciers and alpine terrain. We have been using different type of equipment. We are building drones ourselves, so we have several prototypes, and we are also using commercial off-the-shelf drone, including DJI Matrix 300. And we are using different sensors. Here I will mostly show results on photogrammetry, LiDAR, and also GPR, high frequency and low frequency GPR. So a little bit of LiDAR. So we are in the western fjord of Norway. You see that there is a road here between two tunnels, which is just above an avalanche path. There are some protections for the avalanche, but it's not always enough. This is a big avalanche release area, up to 1,300 meters high. And what our colleague of Norwegian Public Road Administration did in the winter 2023 is that they been recording a lot of LiDAR data to scan this avalanche release area. So that's beyond visual line of sight flights. 24 days of LiDAR campaign. So basically the pilot is at the road here, it's flying the drone, recording data in this area here in the top. And then that's the kind of results that we get. So the background map here, it's an airborne LiDAR model that we have all over Norway. And then we get the new model with the snow here. So the baseline map is without snow. And then we get the new model with the snow calculated from the point clouds, from the LiDAR. And then we can calculate the snow thickness. And this kind of data, so we have 24 days of data like this. This has been given to the avalanche forecaster, and they have been using results like this. For example, they can look at the change one day to each other. Here we see for example, there have been a blasting and avalanche release in this area, so they can see the size of the avalanche. They can also look at the snow changes. Here there have been a lot of wind, a lot of snow erosion, so we see that there have been more than 1 meter of erosion. So the forecaster can use this also to assess the avalanche hazard. Just to come back, you see here we are above the road, so that's the avalanche release area here. The road is the bottom right here. And we can look at the snow depth, for example, and this is very useful to estimate the potential avalanche size. So here we have more than 7 meters of snow. And then the avalanche forecaster can use that for better forecasting. And we did some testing with avalanche forecast without the storm data and with the drone LiDAR data, and we see quite a big difference into the accuracy of the forecast. So it has been shown to be very useful, and that was the first very promising test. Very quickly on drone photogrammetry, Robert has been talking about this, so I don't go too much into detail. But we have been working a lot on improving the processing workflow, and you see here on this line here above cars, you see that you can increase quite a lot the accuracy with proper processing. Don't have time to go into details, but that's also an important thing if you want to boost the accuracy, that you process your image correctly. Little bit on GPR data. I don't have time to show all the slides here, but I can come back if there are questions. So that's a drone GPR survey in Storlidalen, one of the first tests we did actually. We are flying 1 meter above the ground and 1 meter per second speed, and we see at some locations we come very close to the ground, even if we are going downward, but we still have like very good results, like snow surface at the top and snow ground interface, and also some internal layers. So here we have a very specific site where we have almost no snow at the top, and then there have been some wind transport and up to 2.5 meters of snow in the middle here. What is also very interesting for avalanche forecasting is to look at layers and layer characterization, and this has been touched upon a little bit by Robert just before. We try to correlate the data we get with snow pits. Here it's 2 surveys, the exact same location at 2 weeks interval, and we see quite some changes in the layering inside the features. The ground here that we see, the main reflection here is the snow to ground interface. That's quite similar, but the layers that we see inside the snow are quite different, and especially they correlate very well on this second profile with a rain crust, like a layer which is close to the surface here, and even if this is not a weak layer, that's usually correlated to weak layers because there are like some snow metamorphosis happening around these layers. And what we conclude also from this is that data availability is very good, and we can look also at time lapse. So that's exact same survey. We just pick the layers here, and then we can look at the snow thickness change. It's not exactly the snow thickness here because there might be also change in the snow density, and this is affecting the wave propagation time shift. But that's a good start, and we can look at the changes in the layers as well. So that's very useful also for the avalanche forecast. If I have just few minutes left, I want to show a little bit on another site where we've been working. So this is more on glaciers. This is in central Norway, near Jotunheimen, very small glacier. They call it ice patch actually. This will most likely disappear quite soon. There was like up to 60 meters of ice in 2015, probably a lot less now. We see in the summer here, and this is in winter what it looks like. It's about 200, 250 meters up from bottom to top, and we did like a full-scale survey, like this is this red survey here. So this is basically like this, with one set of battery, we managed to fly 25 minutes, and we cover 2.2 kilometer long survey. It was quite challenging flight, like blue sky, but a lot of wind gusts, 10, 12 meters per second wind gusts, and we were flying at 3 meter altitude and 2 meters per second flight speed. So with 20 meters between lines here, we cover almost 4 hectares. Just to give you an order of magnitude of what we can cover with just one set of battery. Of course, you can switch batteries and cover the full glacier if you want, but just if one set of batteries, that's what we managed to get. And we get this kind of results at all the profiles from top to bottom. We have the snow layer on top, and then the glacier ice. We measure approximately 7-8 meters of ice in this I think it's the bottom where we have the most of ice. So that's quite good results, and it's quite interesting for like large-scale glacier mapping for both mass balance to look at the top of the snow, but also to look at the ice thickness and monitor this over years and see the changes. Yes, I guess that's all. I have a lot of other slides, but I can show them if there are questions, maybe. Otherwise, it will take too much time.
Thank you, Bastien. Thank you so much. Yeah, there are some questions. And yeah, let's start with LiDAR and photogrammetry related questions. What is the model of LiDAR specification that you are showing?
So we are using the DJI LiDAR, I forgot the name, but it's like quite a basic LiDAR. It's not very high accuracy. We actually been doing some testing of repeatability, and it's not very good. We see quite some errors between just two surveys at just 1 hour interval. We have quite some differences, like several centimeters up to tens of centimeters. So that's good to keep this in mind. Of course, there are a lot more expensive LiDAR with a lot better accuracy. But the one we were using is like the DJI, the standard DJI LiDAR. I forgot the name, but
L1.
L1, exactly.
Okay. Yeah, but sorry for interrupting. DJI L1 for the snow can be a good option because it provides usually access points for normal surfaces, but for high reflective surface like snow, it may be one of the best options.
Yeah, so I've shown that we have been flying like that's our colleague from the Norwegian Public Road Administration have been doing these flights, but 24 days during winter in Norway. So you can imagine that it was not 24 days of sun. So of course we have been doing photogrammetry, but getting good light conditions to get good results, it's more challenging. And here's the LiDAR survey we did some in when it was snowing. Bad conditions, and we still managed to get results. So that's also something to be aware of. They need data to decide if they have to close the road or not, and they need data when it's bad weather, when the snow is coming, when there is wind. So they want to get data when conditions are not optimal. So LiDAR is the only option in this case.
Yeah, thank you, Bastien. Thank you for this clarification. a lot of questions actually about software. What kind of software do you use? I believe that was that this question was to the slides you shown this this avalanche prediction.
Yeah, for you mean for LiDAR or for GPR?
I don't know. Probably that would be better if you can go through all the software that you use for your data processing. Photogrammetry, LiDAR, data sharing, data processing, everything.
Okay. Yeah, so LiDAR is most of the LiDAR, at least all of the one I know, are like it's proprietary format, so you must use the software provided by the producer to get your point clouds, and then you can use whatever software to visualize your point cloud after that. For the rest, for photogrammetry, GPR, we like to work with open source libraries. So that's mostly based on different Python libraries, mix of different things. And we like to work with open source because let's make science reproducible. So we are like a research institute, but there are a lot of commercial software as well, which are very good. And maybe the learning curve is also a bit faster if you use commercial software. But when you have a good workflow with open source software, then it's very efficient as well, and you have control on everything. So most of our processing software is based on Python and R libraries.
Yeah, thank you for this clarification. Robert, and you, what software do you use for data processing and like for GPR, photogrammetry, and LiDAR?
Well, for data acquisition, of course, UGCS. And then since 2015. And
wow.
And for data analysis, in most times Pix4D, and for the pre-processing afterwards, Cloud Compare, QGIS, and also sometimes some CAD systems, but there I'm not the expert. I have to go to the colleagues. Yeah. So we started comparing different options in 2015, 2016, and Pix4D is working well. So why should I change?
Okay, now I suggest let's talk about GPR, because I see there are multiple questions about GPR, and that would be great if we start with a short maybe step backward. There are several GPRs in the market. At least we offer 4, 5. What is the best GPR model for this snow and ice research, and how to choose the best solution for this research?
Well, snow and ice are two different kinds of you want to analyze.
Oh yeah. Sorry. I'm not a professional. Sorry.
Yes.
For me,
so I think
if it's winter, then it's snow and ice.
No. Also, so from our side, it's also different time when you're analyzing ice and glaciers. It's completely on another time than when you're analyzing such snow stuff. And here for the snow stuff that you, for example, see here on the right hand side, we're using high frequency antennas. And for the glacier stuff, you need the low frequency because you want to get deeper, but you again don't want to get so much in detail. But I think Bastien also can say some more information because he's more the geophysics expert.
I guess you're right. It's always a compromise between penetration depth and resolution. And of course, if you want more resolution for snow, look at the layers. You need higher frequency antenna. I think there are little options on the market, not many options. It's mostly because the sensor must be light enough to be mounted on a drone. I think that's the most challenging part. And also, you have to keep in mind that you will never get data quality which is as good as if you are acquiring data on the ground. You always lose some energy. You lose in resolution, in spatial resolution. So always to keep in mind that if you can do a GPR survey on the ground, if it's safe, it doesn't take more time, then do it because it will be better data quality than if you use your drone. But of course, in some specific locations, like going into avalanche terrain, going onto glaciers, if you want to cover large area very quick, then drone GPR is a very good alternative.
Okay, thank you. Alexey, do you have anything to add?
Everything is right. So you need to select the frequency depending on the required penetration on medium, of course. Bastien, I would ask you about your last demonstrated project. Why you used 150 megahertz for the estimated depth less than 20 meters? So for me, it should be 400 or 300 megahertz.
Yeah, you are correct. It was overkill. We could have used. I think it was like we had like a very wet layer of snow on top, like 2 meter, 3 meter of very wet snow. So with the 1 gigahertz antenna, we didn't go through this layer. With 400 mega, we had like this layer, this snow layer on top with no problem. So that's why we just wanted to test with 150, and we were not very sure also about the ice thickness. We just had data from 2017, which was at least 10 meter more. It was mostly a test, but of course, we could have used 300 mega maybe to have a good, better resolution. You are right.
Yeah, and one more comment actually for the potential quality of the data for terrestrial and airborne surveys. If you can walk, dragging sled or cart with a constant speed, of course you will collect better data. But in situations like here, just on that slide, that screen, you will not be able to collect any data at all, most probably, from surface. I had experience of attempts of collecting data on glacier from the ground. So after few hours, we stopped that attempts and continue with drones actually.
Yeah, I completely agree. Just one thing to take into account that seeing this picture, it's in steep terrain. You have also to keep in mind that especially if you use a shielded antenna like this 1 gigahertz, you have to keep in mind that your like the directionality of your source is not parallel to the ground. So this is to be taken into account as well when you process your data. And when you're on steep terrain, you have your antenna which is just sending energy straight down. Of course, your drone might be a bit tilted, but you can correct for this. But also, you have to correct for the steepness of the terrain. And that's not always straightforward to do that.
Let's continue with GPR questions. There's a question from Koskan. Sorry if I mispronounced it. How many types of GPR antennas have you used, and what was your maximum inspection depth? Robert, Bastien?
So we have used 2. So that one that you can see here on the slide, and the long frequency antenna. And with this, at the moment, we got 60 meter in depth airborne. So I don't have all the information from my colleagues what they used ground-based, but in the air, that's what we have used.
Bastien, for you, what was the maximum?
Same answer. We use 2 types of GPR, one high frequency for the snow and one low frequency for ice. That we will test also for other type of media. And in ice, it depends if it's cold ice or like polythermal glaciers, like with liquid water, and it depends on the size of the antenna, but with 75 megahertz, I think you can go down to 100 meter, maybe a bit more. It depends on the type of glacier.
100 meter. That's not bad. Okay, and do you make horizontal and vertical GPR slices and 3D cube, so to say? The question from Sophie.
Yeah, you can do that if you have you can do time slices if you have like a flight pattern which is close enough, like your flight lines are close enough. There is a nice paper which is just out in a Journal of Glaciology from people from University of Lausanne, where they did like very high dense surveys on some glaciers in Switzerland, where they have like, I think, 1 meter spacing between each line. It's very good data sets, but takes a lot of time, several days to cover a small part of a glacier. So of course it depends what you want to achieve. If you just want to do like mass balance calculations, it's probably good enough. It's already a good improvement to just have some lines like every 20 meters compared to what glaciologists are usually doing, just taking a probe and just probing the snow depth at like 10, 20 locations. If you have like snow depth lines every 20 meters, it's already a huge improvement. So it depends what you want to achieve and how much time you want to spend on this.
And for the vertical and horizontal, it also really depends on how steep is your slope where you want to fly, and also if it's irregular or if you have really a lot of changes in the slope. And there we made the experience that it's easier to fly horizontal to the slope than going up and going down.
Mm-hmm.
But I think also the software will support some help for these challenges in future.
Yeah.
I think so. Alexey told me.
Yeah. So for the data, sorry, Alex, for the GPR data processing, using commercial software for GPR data, unfortunately, no one software, what I know, supports import of the ground elevation data. So imagine that you need to, you want to build a 3D model of snowpack on exactly that mountain, what we see on the picture. So drone is flying more or less parallel to the snow surface. So in GPR data, of course, with some deviations, we will have a horizontal line of the snow surface. If we want to build 3D model, we need to align all GPR data according to the elevation of the snow in a snow surface in the space. Problem is that no one commercial software for GPR data supports such operations with the data.
No, but there are some, it's quite standard in like for seismic processing to do this kind of thing. It's called the migration, and it's so it's not in GPR commercial software, but that's something that can be used from other kind of software from seismic processing, and it's not very difficult. The only challenge is that you need to know the wave propagation velocity in the snow, which is usually not constant, but as a first order approximation, you can just use a constant velocity and do a depth migration with that, and would be a good start.
Thank you. But if there is there any, I don't know, more or less proven workflow? I mean, in terms of data processing for GPR data, because we had a lot of questions from during the registration, like what would you recommend for GPR data processing? What is the most I don't know, straightforward GPR data processing workflow? Any tips and tricks here?
I guess it depends a little bit what you want to achieve. If it's just for visualization, it's quite simple. Basically, GPR data, you get a lot of noise. It's like electromagnetic wave propagation, so you get electromagnetic noise. But this noise is quite constant, so it's easy to do just some filtering or just remove the background noise, and then you can just increase the amplitudes of the late arrivals. That's called amplitude correction or veil. And just doing these two things, maybe with a bandpass filter, this you just get like a good visualization of the data. Just doing these 3 steps. Like hundreds or thousands of publications and manuals and explaining this kind of things. That's quite easy to do. Then if you want to do more quantification or more like advanced work, then you have to be a bit careful on what you are doing. And again, there are a lot of I don't have time to detail all of this, but there are a lot of publications on these topics, and you can get in touch with me if you want more details.
Oh, yeah, thank you for the suggestion. Yeah. Also, data-related question: how is the data checked for accuracy, and is RTK or PPK used for processing? I believe that's wasn't not for GPR, but more for photogrammetry and LiDAR.
Well, on all data that we have is checked. So photogrammetric data is checked with GCPs and checkpoints, of course, and on the flights with the GPR we are using RTK correction if possible. If not possible, we are using PPK correction, and also there we are checking the data with our snow profiles and so on, and measure snow depth measurement.
Bastien, and in your experience?
Same for us.
Same for you. Yeah.
Actually, it's interesting. We did some survey with non-RTK, and we had the RTK on the drone, but some problem with the base station. And we see it was a survey, GPR survey. There was a lot of small boulders on the ground, and we see quite some variation. If you just like few tenths of centimeter away, you don't see this like the diffraction hyperbola from these boulders on the data, because the drone is just I think on the specs on the DJI, if you don't use the RTK, it's plus minus 30 centimeters, something like this accuracy. So it's highly recommended to use the RTK or PPK if available. So.
Okay. Now let's talk about these extreme sometimes conditions. I mean, I love mountains, but for research, probably not the best place to be. All this low weather, wind gusts, and everything. What are your recommendations here? How to prepare for all this, and what should be taken into account when planning all these missions and research? I mean, shorter battery time, wind resistance, lower pressure altitude, all these things.
Well, so for our side, so my coldest starting was at minus 20 degrees Celsius, and also with wind in average was 50 kilometers per hour, and it works very well. The only thing you have to look up is how fast the gusts can be, because this can be really challenging. But if you have a really stable wind, it works also with 50 kilometers very well. The self-heating batteries on the Enterprise drones are really a fine thing, that you don't have to care so much about holding the batteries warm, but also before this was for flights, put all the batteries into your pockets, and then it's possible to fly. And also important is just to be safe on yourself, to just have a lot of clothes to stay warm and warm drinks.
Thank you, Robert. Bastien, for you, your recommendations?
Yeah, I totally agree. Usually the weak link is a drone pilot, which getting cold, like standing up for a few hours in the cold. Just one thing about the wind and wind gust. If we record data with GPR, we have to be quite close to the ground. So here you have to be a bit more careful on together with respect to wind gust. But we have been flying up to 10-12 meters per second at 3 meter altitude, I think, and it was fine. But if you record data for LiDAR photogrammetry, you are a lot higher, so it's usually not a big problem. And we operate in Norway, so it's dark, bad weather most of the time. So it was quite challenging, but it worked many times. Just want to add maybe one thing about we were discussing about photogrammetry versus LiDAR. you get good data with LiDAR when it's bad weather, but it's also that you have more chances to crash, and it's a lot more expensive to crash with a LiDAR than to crash with like a standard RGB camera. So that's something to take into account as well when you fly in harsh weather, that maybe you don't want to risk crashing your very expensive drone and sensor, and maybe you use something like a cheaper drone and get maybe a bit less good data, but it's less risky as well.
No, good idea. Good idea. Okay, we have 3 minutes left, and let's talk about your vision of the future and your forecast. How do you think how all this will evolve in the nearest, let's say, 3 years and 5 years?
Yeah, well, the hunger solutions are getting better and better. I'm hoping that we can use such sensors also in hunger solutions in the next years, and I think then this can help us really a lot to get more information about, for instance, snow structure on avalanche slopes over critical infrastructures. It can really help a lot, and of course the sensors and the platforms are getting lighter and lighter and smaller, and also this will help us to fly in different terrains.
Robert, Bastien, what do you think?
Completely agree as well. This drone garage, it's very useful in countries like Norway, where you have like a lot of remote places, difficult access, and that's one of the vision as well of the Norwegian Public Road Administration, to have like drone garage at given locations that can record data autonomously, and then the next challenge as well is to process this data in almost real time and interpret this data also automatically. But that's another story which is not directly related to drone, but that's also, you get a lot more data, but you need to also some processing power to interpret and process all of this data, because otherwise they are useless. So, but I see that it's good short-term future. That's you will get more and more drone data, and you will have to find good solution to process and interpret all of this.
By the way, also drone-related question and drone fleet-related questions. Why do you build your own drone? I mean, Bastien, your custom drone.
Yeah, because there are several reasons, but again, we are researchers. We like to understand everything we are doing. We don't like black boxes. So that's why we are using commercial drones also, because it's faster for testing and so on. But we like to work prototypes because they are quite as good or better than DJI drones, and they are less expensive. It's a lot easier to fix, and we have control on everything, hardware and software, and no black box. So we really like that, but we understand also that's not for accessible for everyone. I'm not the one building the drones; it's some colleagues of mine. But you really have to be into this and to do a good job. But that's quite nice when you have been building your own prototype drone and you fly and you get good data. It's very nice.
Okay, that's clear now. Okay, it seems that's time to wrap up. Thank you again for your wonderful presentations and for all these insights. And thank you, dear visitors, for your attendance today. If you have any questions or ideas or project suggestions to discuss, please feel free to drop us a message, and I'm glad to help you. And the recording of this webinar will be available on our YouTube channel, I believe, in a week. So please stay tuned, and hope to see you soon again. Thank you, Robert. Thank you, Bastien. That was a great pleasure to have you here today.
Thank you.
Thank you so
Very
much.
interesting presentations.
Thank you.
Thank you.
Okay. Bye-bye.